our fourth class, and we're covering this section, second section in chapter 1, linear equations, which I believe most of you are feeling pretty confident about. And then the rational equations, which is the part that kind of drives us a little crazy. This is where you would have probably ended your Math 096 class if you had that recently. It's probably one of the toughest sections to get through and totally understand. Part of it is we still have some of us still have underlying misconceptions about fractions to begin with. So that's what kind of interferes a little bit with today's topic. Hopefully after you leave today, you'll understand some of the ways that we can tackle these types of equations. There's sort of like the longer way, and then there's the shorter way. And I'm convinced that no matter what I do to try to teach you the shorter way, many of you will still rely on the longer way. So we're going to do both ways so that you can see how you can work your way through both ways. So I'm going to ask for a little patience today because some of you have approached these differently. This first one, if those of you who are actually maybe reading the text, at the end of every text, they have exercises that will help you for the next section. And this comes right out of the textbook. And one of the first things that happens here, and I know you may be wanting to finish up whatever you're working on, but I really would like your attention because this is where I'm going to clarify some of the issues that you have. It's not important that you finish these right now. It's important that you listen. So what happens here is when people see this problem, the very first problem, their eyes immediately focus on the fact that the stuff inside the parentheses have denominators. And they go, oh, in order to subtract those, I need like denominators. And then they quickly move to make them common denominators. That's not incorrect. However, it's not the most efficient approach. So if you did that, if you made those into common denominators, and you don't have to write this down, I just want for those of you who did that to see that you might have something like this on your paper, but please don't write it down if you didn't do it this way. That's what some of you probably had that did that. And then some of you went ahead and did this, hopefully correctly. Oops. Okay. Now, regardless of which approach you take to this problem, the one tendency here, if there's going to be an error, is the subtraction of that -4. A lot of people will have a -4 there instead of a +4, so they ended up with -1x + 2. Okay, so that's one little place you should check for what we call a common error, okay? Whenever I see something like this, I automatically do this. I put my numerator, which has 2 terms in it. Now remember, terms are the individual parts of an addition and subtraction problem. Each numerator has 2 terms, and I want to make sure that if I'm going to end up multiplying those numerators by a number, I hit both of them. So that's one of the first little things you can do to help yourself. Now, even though this approach is fine, in fact, now look what you can do. 12 over 12 is 1, so your answer is -1x + 10. You've done some extra work that's not needed. So I just want to show you another approach. Rather than focusing on this, look at what you're being asked to do. You're asked to multiply this quantity. Now, when I say the word quantity, it means whatever's inside parentheses. Okay, we use the word quantity. You're asked to multiply this quantity, which has these 2 terms, by 12. So you use the distributive property. You take 12 and you multiply it by the first term, x + 2 over 4. And then you take 12 and you multiply it by the second term, x - 1 over 3. And notice I can just use one big long fraction bar because with multiplication, the 4 doesn't have to belong to both of the things on the top. I could separate this first fraction out and call it 12 divided by 4 times x + 2 if I wanted to. So immediately when you do this, you see that this can be reduced to the number 3. 12 divided by 4 is 3 times x plus 2. And then immediately you can see, hopefully, that 12 divided by 3 can be reduced to a 4. And now you're not dealing with fractions at all anymore. You've eliminated all that fraction work. But notice what you get. 3x plus 6 minus 4x plus 4, which was exactly what you got in that first, when you originally did all the work of changing them to common denominators. So in both situations, you wind up with exactly the same answer. But they're different approaches, they're different processes that go on. Okay? So what I'm hoping to do today is when we look at equations, we don't need to change everything to a common denominator. And that's going to be the sort of the habit that I'm going to try to at least have you see today could make life a little more efficient for you. However, this is my caveat. If you need to rely on changing everything to common denominators and doing more work, that's okay with me. I just want you to see both methods. So that happens down here with this one. This is probably one of the easiest types of rational equations you can see. Why? Because every single denominator is a constant. It's just a number. And I'm also going to show you how you find the number they all divide into. And you say, oh, come on, Kavanaugh. I know 12 is a number that 4, 6, and 3 divide into. But what I want you to see and understand is the concept behind it. So when this changes to x plus 4 and x minus 6 and 3x on the bottom, you can use the idea that you used with numbers. So I'm going to quickly review this. But I'm going to do it with numbers, so hopefully you get a sense of what you will do when these all become algebraic expressions on the bottom instead of numbers. Okay, so what we're going to do here is we're not going to change these all over to 12ths. You could. I want to show you the more efficient or the quicker approach. And the reason why we have another approach is the very fact that this is an equation. It's not an addition and subtraction problem. If it were, you'd have to change to common denominators. But with an equation, you have a very powerful tool available. And that is, you have every right in the world to multiply both sides of this equation, both sides, and everything on both sides, by 12. Okay. If that was just an addition problem or a subtraction, if I was just looking at the right side of that equation, I'd have no right to multiply each piece by 12. I'd make it 12 times bigger in value. But because it's an equation, I have the right to do that. So I'm going to show you the concept behind 12 and how we found 12, even though we know it's 12. So in this case, I'm going to call 12 the least common multiple. You call it the least common denominator or the lowest common denominator because when you're adding and subtracting, its place is in the denominator. The 12 that we're using today is being used as a multiple. We're multiplying both sides of the equation by it. So even though it's exactly the same value, the name I use is different. How did I get 12? Well, what I did is I took, and you notice on your desk, I'll get a toolkit for table 1. You all have a toolkit. I advise you to take out 2 or 3 different colored pencils, not necessarily right now, but to help you work through today, because I find colors really help you see what I'm about to do. So I take each denominator, and right now, each denominator is just a single number. And then I factor each denominator into prime factors. So 4 is not too tough, it's 2 times 2. And since each factor is the same, I keep the same color. What is 6 as prime factors? 3 times 2, right? So since I have a 2, I'll use red. And since I have a new prime factor, I'll use a green color. And 3 is prime already. Ooh, yay, no work there. Okay. So if you were doing it this way, one way to describe the common multiple in words, it sounds really complicated. You represent each prime factor. How many different prime factors do we see here? How many different colors do we see? 2. So you represent each prime factor. And in this case, we have a red 2 and a green 3. We can't just write each prime factor down because we have a one denominator that uses 2 2's, right? It has 2 2's in it. So the language that people use is actually more complicated than what you do. The language says take each prime factor the most number of times you see it in any one denominator. I see a 3 once here with the 6, and I see a 3 once by itself. I only have to represent it once. I see a 2 here twice, and a 2 here once. So the most I see it in any one denominator is twice, so I have to put a 2 on it. Okay? So that's how I get my 12. It's 2 times 2 times 3. The nice visual I like for this is the following. I take 4 and I write it as 2 times 2. I take 6 and I write it as, I borrow one of the 2's and I go like this. And then the 3 is there. The 3 is right here. It's in its own little orbit. Look what happens when you multiply across. You get that common multiple. So when these become things like x plus 2, x minus 2, and x plus 3, you can use these circles, or you could use this method to find your lowest common multiple. Now, another way to find the multiple is just to come straight down like this and represent each multiple. That's just another way to do it. Okay, so this would take me a couple of classes in 096 to do. So this is just a quick review for you. All right, we found the lowest common multiple. What the heck do we do with it? Well, I don't use it to create common denominators. I use it to multiply each side of my equation by that multiple, and that's going to make life very quick. So there's my expression on the left-hand side of my equation. I'm just multiplying it by 12. And the first term on the right-hand side of my equation, I'm going to also multiply by 12. And I just put one big fraction bar over between the numerator and denominator. And then the next one, I also multiply by 12. Okay, that's my first step, or my second, because I had to find the 12 to begin with. Now look at how beautiful it is. You chose 12. So each one of those denominators are a factor of it because it's a multiple of all 3 of them. So voila, you get this beautiful reduced fraction for each one. Yeah, the middle one should be 2. Thank you. All right. So now look what you have. 1s in every single denominator. Woohoo! So now it's just a baby linear equation. You've got 3 times x plus 1 equals 2 times 1 plus 4 times 2x minus 1. And now you all can solve that equation because you've now made it into a linear equation. All your denominators are 1, so it's 3x plus 3 equals 2 plus 8 minus 4x. 3x plus 3 equals 10 minus 4x. 7x equals 7. X equals 1. You're done. Okay? Your book asks you to put all your answers in a solution set. So when you put this in my math lab, you'll have those curly braces with the number 1 inside of it. Okay? So maybe I've convinced you, maybe I haven't. If you did it all as common denominators, I want to show you a little way out of it because sometimes students do all this work and then they don't know what to do with it. So sometimes students end up with something like this. They end up with that on the left-hand side. Check your work and see if that's you. And on the right-hand side, you end up with something like this. You get there and you stop cold in your tracks and you don't know what to do. Okay, so think about this for 1 second. We're asking what value of x makes the left side equal to the right side? Look at the denominators. I mean, if I wanted to, I could have put 1s over all of these. It's not necessary because 1 is equal to 1. I don't even have to pay attention to that. When you have something like this, the 12 is already equal. There's nothing to do with that 12. You can literally totally ignore it. All you have to solve is 3x plus 3 equals 10 minus 4x. That's it. That's exactly this if you made all of these into common denominators instead of the approach I used. Okay? Now, here's the other thing I want to show you folks. Let's go back to what I just had a minute ago, because this is one of the weakest parts of our education. Does anybody know the special name for this equation? When you have a fraction on one side equal to a fraction on the other, or a rational expression on one side equal to a rational expression on the other? Give me a P. Give me an R. I was never a cheerleader. Give me an O. Give me a P. Give me an O. Give me an R. Proportion. This is a proportion. I got some smiles out of you. There we go. A proportion always looks like this. And the easiest way to solve a proportion, notice it's an equation, it's not a multiplication problem, is to use this cross product idea that AD equals BC. So some of you could have solved this by just doing your cross products. That's just another way around this. And the only reason I'm showing you that is because some people put the right side together and make them 18ths. So they have something over 18 here, and they have x plus 1 over 4 here, and that way you could just use cross products. There's like 1,000 different ways, not literally, but there's a lot of different ways of doing this, and you all do something differently. I'm hoping to convince you with this method here today somewhat, that it's easier and more efficient. All right, let's take a look at our very first problem in the teaching demo. So all this language up here in number 1 is my hope to convince you that yes, it's a lot easier to solve these equations by getting rid of the fractions. So let's see where we want to start today. All right, this first thing right here, this first description is very important. I call this step 0, but it's the step to do. I call it step 0 to help you remember the most important thing about these equations is you cannot have a denominator that equals 0. So you have to look at the domain for each one of these expressions. This is what you had in your activity on Wednesday. The very first part of your class activity was the domain for a rational expression. So if we look at 7 divided by 2x, we have to think about what value of x will make that denominator 0, and we need to exclude it. So what value of x makes that denominator 0? Yep, Cyrus? Excuse me? 3.5. For this one here? All right, so we want to know, when does 2x equal 0? I'm trying to remember what makes you think 3.5, because if I put that equals 1, right? So we want to know what, I'm going to stick with you, Cyrus, because I'm not giving up on you. But if I just say what makes 2 times x 0, right? So that would make the first denominator 0. Guess what? It makes the second one 0. So 0 is an excluded value. This step here goes with, I wrote the general steps. This doesn't apply to today, to this example, but it will apply to the one on the reverse side of the page. So How do we find the lowest common multiple? What is the lowest common multiple of 2x, 3x, and 3? Part of that is correct. I do need a 6, but I also need an x because I see an x. So bear with me while we go through this again. This is where your colors come in. Let's write each denominator down all by itself. Here's each denominator. They're already factored because it's 2 times x. So 2 is prime and x is prime. So there are the 2 prime factors for the first one. I see a 3. Well, I don't see a 3 anywhere else, so I have to separate that out with a different color. And then I see an x, which gives me a green x. And then I have my 3, which is prime. So here's my LCM. 3 times 2 times x, which is 6x. Or with my circles, here's my first circle. I have a 2x in it, 2 times x. 3x, to get 3x, I borrow the x from my first denominator and put in my prime factor 3. And there's my third denominator, 3. So if I multiply straight across, I get 6x. Okay. So Olivia, do you understand why we need an x as well as the 6? Okay, because it's one of the factors you see, okay? All right, so we're going to multiply every single one of these terms on the left side and the term on the right side by 6x and see what we get. So let's do that. So I have 6x times 7 over 2x. So that looks like this, 6x times 7 all over 2x. And I'm going to multiply 5 divided by 3x by a 6x. So it looks like this. And then I'm going to multiply 22 divided by 3 by 6x. And the only reason I can do this is because I have an equation. I do not need to create common denominators. But I will create common denominators. They're just going to be 1. So now look at that first fraction. Do you see any common factors to the top and bottom? What do you see? What common factor do you see right away? In this first one right here, 6 times x times 7 over 2 times x. What do you see as a common factor? The x, yeah, there's one form of 1 right there. There's one form of 1. And what else do you see as a common factor? It's a little bit hidden. What's common to 6 and 2? 2. 2 is common to 2, and it's common to 6, and you have 3 left. So you have 3 times 1 times 7, which is 21. Hey, I like looking at that a lot better than a fraction. And in the next one, what's common? The x's, x over x creates a nice big factor of 1 that you're dividing out. And 6 and 3 contain a factor of 3. So you divide each by 3, you get 2. And so now you have 5 times 2, which is 10. And then on the left side, the right side, you have an x in the top, but not one in the bottom. But you have a 3 in the denominator, and you have a 3 that's a factor of 6, which leaves you with a 2. So that equals 44x. Yep, you just keep it. Yep, because there's no x in the bottom to divide into it and create a 1. Yep. Nope, you just leave it right there as it is. Okay. So voila, the fractions are gone. We don't need to use our distributive property. So we combine like terms on the left side and we get 11 equals 44x. And then we solve. We solve the equation. So we divide both sides by 44 and we get x equals 11 divided by 44 and we reduce it and get 1/4. Okay. And you say, is that one of the numbers that was excluded from step 0? And you say, nope, it's perfectly legitimate, but you should always check. You should always check it to make sure you did it correctly. Questions on that before we move ahead? Yep, Olivia? Yes, totally cool. Yep. You can change everything to 6x in the denominators if you want and do it that way. I don't care. It's just taking you longer, that's all. Questions before we move on? Okay, let's take a look at the next one on the number 3. 3 looks a little different, doesn't it? Now, if you don't want to use my method, it's going to get a little complicated if you don't, first of all, find the lowest common either multiple or denominator, and you just multiply all these denominators. It's going to get really yucky. So let's just take our time right now. In order to find the excluded values, there's a step you have to do, which we didn't need to do with the one we just did, and that is everything has to be factored into its prime factors. So the first denominator is already done. Your first denominator is just x, and that's prime. That's done. The second denominator is 2 terms. You have x squared and you have the term x, and you're subtracting them. So anytime you see something like this, the very first thing that should pop in your mind is greatest common factor, greatest common factor, greatest common factor, to factor it, right? Greatest common factor, and my teacher's a kook. But it will help you, because what is the greatest common factor here? That would be x squared minus 1. Just x, right? That's the only thing common to both. And we've decided to call x the color black. And then whatever's remaining, what other factor that's part of this, will be a new prime factor. So how many different colors do you see here? 2. How many factors will I have in my denominator? 2. X. So to get my LCM, I need an x as a factor, and I need x minus 1. Okay? That's all I need. Now, I can look at this and I can tell what my 2 excluded values must be. X can't be a 0, and x minus 1 cannot be 0. So x cannot be 0 and x cannot be 1. Those are the 2 excluded values. So what does that mean? You do all this work, you come down, you get maybe 2 solutions, and if one of the solutions, say x is 0 or 1, you cross it out and you say, no way, it's an extraneous solution. All right, so I start off very simply by factoring all my denominators. There I am. I have identified my lowest common multiple to be x times x minus 1. And yes, you may change every single denominator, every single term, so that it has a common denominator. I'm not going to do that. I'm going to take this multiple and multiply each piece of that equation by it. So I'm going to say x times x minus 1 times 1 over x. And I'm going to take x times x minus 1, and I'm going to multiply it by 1 over x times x minus 1. So I'm going to take my multiple and put it in a different color. And that's why I gave you those different pencils. So you can see the original part of the equation with its now equivalent equation. So I did the left side. Both of the terms on the left side are multiplied by x times x minus 1. And now I have to multiply my 5, which is on the right side. We can't forget about 5. That has to be multiplied by x times x minus 1. So the whole purpose of doing this is to clear out those denominators and make this equation have just a 1 in the denominator. All right, so if I look at my first term, here's my first term, I see I have a common factor of x in the top and bottom. So there's my form of 1 that I can reduce this by. And so what am I left with? X minus 1 times 1. Hey, cool, it's x minus 1. So I'm left with x minus 1. I can drop the parentheses, they're not doing anything. So I can just write x minus 1. And then my second fraction, my second term here, yeah, I can cross out everything. The entire denominator is contained in the numerator. So that's a nice form of 1. And I'm not left with nothing. What am I left with? 1. And that's where some students make their mistake. They cancel everything and they're forgetting that they're creating a 1. And 1 times 1 is 1. So my second fraction is 1. And now on the right-hand side, I have 5x on the outside, and I need to use my distributive property to get 5x squared minus 5x. Anybody have any questions on how I got to the purple equation? So what would we do now with the purple equation? Combine like terms. So -1 and 1 leave me with an x, and I have 5x squared minus 5x. What kind of equation is this? Quadratic. Yep. So there's multiple ways to solve quadratic equations depending on the form. You could always use the quadratic formula if you wanted to. We haven't covered that yet. So I'm not going to be asking you to do something we haven't officially covered. But we have covered factoring in section P5 and also in your first day handout. So to solve a quadratic equation, the first step you have to remember is to set everything equal to 0. So you're going to subtract x from both sides, and you'll have 0 equals 5x squared minus 6x. You have the quadratic term, which is 5x squared. You have your linear term, which is negative 6x. How are you going to factor this? What do I want to hear you shout out loud and strong? How do you factor it? Come on. How are you going to factor that right-hand side? Pull an x out. What's the pulling the x out called? Oh, I know what it's called. Come on. What is what? What is a star like? Oh, what's it start with? Give me a G. Greatest common factor. There we go. Woohoo! All right. Factor by using the greatest common factor. I tell you, this is going to be your best friend, this greatest common factor. So we pull out the x, as Evan said, and we have 5x minus 6. And now we have a multiplication problem on the left side that's equal to 0. So we know how to solve that. We take each factor and we set each factor on the right-hand side equal to 0, and we solve each factor. Well, there's nothing to do with x equals 0. That's already done. And we need a couple of steps here to solve this one. We get x equals 6/5. So do we have 2 solutions we put in our solution set? No, I see 2 right there. Oh, I can't have 0, right, because it was excluded way back at the beginning. So the only solution here is 6/5. Right, that's my solution set. Okie doke. So have fun. You've got lots to do for your class activities. You will not be bored or sitting around twiddling your thumbs today, I promise you. And please ask for help if you need it. I'll be happy to help you.